So those are all the different ways we can change Q. And now we need to add one more shift, and that is a concern of shift in temperature. So you might remember from the very beginning when we first introduced K, the equilibrium constant, we said whenever you define an equilibrium constant, you always define it at a particular temperature. And this is because the equilibrium constant is temperature dependent. And so when you change the temperature, you don't just change the Q, you change the entire value for equilibrium, you change the value for K. So without getting too crazy, we'll just say the temperature affects the reaction rate, both the forward and the reverse reaction rate. And we know that at equilibrium, the forward and reverse reaction rate need to be equal. So if we affect the reaction rates, then we're going to change the equilibrium. So if temperature affects the rates, that means changing the temperature changes the value for K. And we'll talk more about this in the chapter on kinetics. All right, so changing the temperature changes the position of the equilibrium. That's like shifting the fulcrum part of the balance beam is moved to a different spot. So if we think about what happens when you change the temperature, changing temperature means you're adding or removing heat from the system, and heat is related to enthalpy. We spent a lot of time talking about that in the thermodynamics chapter. So the direction of the shift of K is going to depend on the change in enthalpy for that reaction. So those things we spent so long learning about in the thermodynamics chapter, they're coming back. They are relevant once again. So we know that there are two types of enthalpy changes. There's endothermic and there's exothermic. So let's look at each of those separately. All right, let's review endothermic. An endothermic reaction is one in where the change in enthalpy is greater than 0, where the heat is entering the system. And usually we represented this by drawing a box for the system and having the heat arrow going into it. But another way we can represent it is by writing our reaction as reactants go to products and adding heat into this equation. So if heat is entering the system, if it's adding to the system, we can write heat as a reactant because it's entering and it's being used to make the product. And so now we can think about how the K value is going to change based on how much of this quote-unquote reactant we're adding. So if we increase the temperature in the system, how is that going to affect our equilibrium? Remember, this is our equilibrium constant, products over reactants. Okay, so if we increase the temperature, that's like adding a stress to the left side, right? We're adding a reactant, kind of. And if we add a reactant, the balance beam is going to push towards the product side. Going to be a shift right. So if we think about how that's going to affect the equilibrium constant, shifting to the right decreases the amount of reactant and it increases the amount of product. And that means our value for K is going to increase. All right, so if we increase the temperature, we increase K for an endothermic reaction. You can probably guess that the opposite is going to happen if we decrease the temperature. If we decrease the temperature, it's like removing a reactant. And when we removed a reactant from the balance beam, that shifted it higher on the left side. So the system shifted towards the left to adjust for that. So if we look at how that shift will change our K, shifting towards the left is going to increase the amount of reactant. It's going to decrease the amount of product. So our K value is going to decrease. So if you decrease the temperature, you decrease your K for endothermic. We're going to put that in a box, actually, so we don't get confused. All right, so again, these only work for endothermic, and everything is different in an exothermic. These are not things that you should be memorizing because it's too difficult to memorize which situations shift left, which situations shift right, which ones depend on other things. It's better to just try and figure it out like we're doing here by adding things into the reaction or drawing the balance beam picture to help you remember. All right, an exothermic reaction is one in which the enthalpy change is negative. Heat leaves the system. If we write our reaction this time, reactants, go to products. If heat is leaving the system, you can think of it as something that is produced after the reaction happens. So we can add heat over here on the product side. And now we can look at what happens when we change the temperature. If we increase the temperature, we'll write a little smaller so we can still fit everything. If we increase the temperature, it is like adding a product. Adding a product causes our balance beam to shift towards the left. If we shift towards the left, the reactants are going to increase and the products are going to decrease. And that means our K value is going to decrease. Okay, so this is the opposite thing that happened for endothermic. For endothermic, when we increase the temperature, the K value also got larger. And for exothermic, when we increase the temperature, the K value got smaller. So that's going to be different depending on whether your reaction is endo or exothermic. So if you are asked to tell someone how K changes with a change in temperature, you have to know about the enthalpy to answer the question. Okay, we'll finish out strong here. If we decrease the temperature, decreasing the temperature is like removing a product. And when we removed a product, that was like decreasing the stress on that side, increasing the stress on the reactant side. So we saw a shift towards the right. And if we shift towards the right, we are decreasing the amount of reactant and increasing the amount of product. So our K is going to increase. Increase K, decreased temperature. So I'm going to be very careful thinking about whether your shift to the system is going to be a shift in concentration, which changes the Q value, or whether it's going to be a shift in temperature, which is going to fundamentally move the equilibrium constant, move the whole balance beam to a different spot. So make sure you try and keep those separately in your head. The way of figuring out the direction of the shift is similar, but the variable that you shift is different. One of them shifts Q, and one of them shifts K. So in the next set of videos, we will talk about how to do calculations to quantitatively figure out how much the concentration of each of the different pieces shifts, in addition to our new qualitative knowledge in this set of videos.